Welcome everyone to Researcher's Desk. Today we have the pleasure of welcoming Docent Paul Glantz from Stockholm University and from the Berlin Center for Climate Research, also board member for Researcher's Desk. And Paul is going to be talking to us about aerosols, particles in the atmosphere, and rapid warming in Europe. Paul, the stage is yours. Welcome to Researcher's Desk.
Thank you. I guess you see my presentation now. Let me see. Okay. Okay. Welcome everyone. So the main focus on my presentation is on a publication that was a study that was published before Christmas, and you see the title of the article: Unmasking the Effects of Aerosols on Greenhouse Warming over Europe. And you see the co-authors here on the right, and it was published in JDR Atmosphere done before Christmas. So what we have done here, that we have first part of it, I would say, we have studied the decrease in aerosols in Europe during the latest 4 decades, and we have estimated a warming based on that. So I will talk more about aerosols and also versus the greenhouse gases. So I will come back to that. But you can see aerosol particles is short-lived, it's a cooling effect, it's temporarily hiding greenhouse warming. So for Europe, it's a little bit history of aerosol particles, more or less, I would say. But the number of warming is relevant for other regions on Earth that have high level of aerosol particles today. I'm thinking about, for example, eastern part of China and India then. But in our study, when we focus on the effect of aerosols, it's very relevant to put it in perspective and to compare it to the total warming in Europe then. And I'm quite sure that you already have heard that Europe is the continent that among the continents is warming up fastest then. So I think also we have some contribution to explain why Europe is warming very, very fast then. I will also refer to the latest IPCC report that came 2 years ago. So that's also a thing that I will talk about. But if I introduce a little bit to the aerosol particles, you have to think about fossil fuel use or emissions from fossil fuel is generating greenhouse gases. It's well known for you, but also generate aerosol particles. The main difference when we talk about the greenhouse gases is that they are stable in the atmosphere. I illustrate this in the figure here. They are evenly, more or less, evenly distributed over the planet, and they are mainly impacting infrared radiation. So they letting solar radiation reaching the ground, but the energy that are converted to infrared radiation, then you have the greenhouse gases that are efficient to absorb and re-emit infrared radiation to the ground. That's the greenhouse effect. Aerosols, as you see here, then you have to think about more that they are impacting solar radiation. So you can see that greenhouse gases more as a gas. Aerosols you can see more as a particle, very small micrometer particles, but because of the particle characteristics, they are influencing solar radiation. Keep in mind now the difference in the distribution that you see here, and the main reasons that we have a regional or local effect from aerosol particles is that they are short-lived. So they mainly impact radiation and climate where they are emitted, mainly over the continents then. So we can talk about 1 week lifetime for aerosol particles, that you could compare with the carbon dioxide that you see in this figure, which impacting climate for 100 to 1,000 of years. So a little bit more on aerosol particles. There are actually two effects of aerosol particles. You can see them if we higher the concentration of aerosol particles in the cloud-free atmosphere, more of solar radiation will be hitting back to space, a cooling effect. But one thing you also have to know is that aerosol particles are involved to forming our clouds in the atmosphere together with water vapor. And if you think about it now, if you higher the concentration of aerosol particles, you will impact the cloud properties, which I try to explain with this figure. So here we talk about aerosol cloud interaction. So beside the direct effect in the cloud-free atmosphere, we also have an indirect aerosol effect, which means that aerosols are also, once again, impacting the cloud properties. So higher level of aerosol particles, also higher the level of cloud droplets that you see on the right in this figure. And this higher the probability that solar radiation will be scattered back to space. Is a cooling effect. So on the whole, we see aerosols as a cooling effect. But now we have to think about what's happened in Europe. I mean, this is illustration that you see in this figure is a historical description in the sense, because we had the other way around at present day. Today, we have reduced aerosol particles to a large extent, and therefore also a lower impact on the clouds. But what I will also show you, when we have this reduced aerosol effect in Europe, we also have this enhanced greenhouse effect, and I will coming back to that. We get the positive feedback of that. We had getting a drier climate in Europe. Now I would like to refer to IPCC report and show a little bit more of this reduced effect from the aerosol particles. And this is then from the latest IPCC report. And this, what you see here is an effect on the radiation. On the vertical axis, we have the in watt per square meters. And all this curve associated with aerosols is on the minus side of the values, as you see, and you see the time period 1850 up to 2015, and I pointing out 2015 just to mention also for you that we still have at least 7 years to play with, because when you take a look at these curves, more or less every curve is approaching zero. And I marked out particularly Arctic region and Europe that we will take a look at now. So the largest reduction in the impact on the radiation and climate, when you take a look at these curves, have occurred in Europe. But still, we have 7 years to play with when we're thinking about that we have a turning point of the aerosol particles and radiative forcing are approaching zero then. So what's the reasons for why we have this strong reduction in the impact on radiation and climate? And that I would like to illustrate with these figures, which shows a very important parameter to investigate aerosols, aerosol optical thickness. And it's very suitable to use this parameter because it's possible to get it from satellite observations. And this parameter is taken from NASA MERA 2 reanalysis. And a reanalysis means that it combined in situ measurement based on satellite observation then and model simulations. And you can see aerosol optical thickness is in this case very much related to aerosol concentration in the atmosphere. So here I have subdivided an average according to aerosol optical thickness on the left for the 80s and the latest decade on the right. So first thing, we can conclude that the air quality has substantially been improved in Europe. So the concentrations of aerosols, as you see in the figure, have dropped very much. We talk about 50%, and particularly for this more polluted region that we have in Europe, Eastern Europe and Central Europe. And the main reasons for that, we use much more of dirty energy from coal power plants in the 80s. So we have get a much cleaner Europe during these 4 decades, but that means also that we have a reduced impact on the radiation once again then, and also reduced climate impact. We can also take a look at the most important precursor to aerosol particle, the gas sulfur dioxide that you see on the left that are forming the aerosol particles in the air. And this study, the trends that you see on the left is taken from Smith et al. And I have marked out trends for Europe, North America, and East Asia. And then you see, particularly for Europe, that we have a really strong drop in the emissions of sulfur dioxide that will highly influencing the concentration of the aerosol particles in Europe. We see for East Asia that we have an opposite trend, as you see here. In the middle figure, I have taken an average according to this parameter again, aerosol optical thickness for Central Europe during the latest 4 decades, just to show you the shape of the trend. And this figure shows that the strongest reduction in aerosol particles occurred in the 80s and 90s. It has continued to decrease during the latest 2 decades, but at a smaller rate then. I should mention in our study that we were published then before Christmas that we have focused on the summer half year. We have taken average according to April to September, as you see here. And the question arises now, how has this influencing incoming solar radiation? And now I will introduce you a new parameter that we have studied. And this is taken from European Center for Medium Range Weather Forecast, ECMWF. And this is the latest reanalysis, ERA 5. You can see ECMWF as a center for collecting meteorology data, temperature, wind, humidity, and also radiation, as you see in the right figure here. And also SMHI in Sweden are delivering data to ECMWF. So what we see when we take a look at the radiation parameter on the right here in watt per square meter, and that is the radiation that are reaching the lowest part of the atmosphere. So this radiation is available to be absorbed by the surface. And then we see a clear anti-correlation with the aerosols on the left, as you see here. And this is for clear sky conditions, which is possible to study based on ERA 5. But we can also take a look at all sky conditions to take a look at the trend in the radiation. We see a larger variability here, but this is because we have a mixture of cloud-free day and cloudy day, and that produce a larger variability. We have also comparing ERA 5 radiation parameter with ground-based measurement, which is taken from the Global Energy Balance Archive, and they are marked with gray squares, as you see in this figure. And here is 4 examples of when we are comparing ERA 5 with this ground-based measurement. And we can conclude here also, we can classify the period that we have before approximately 1980, that we have a dimming period due to the higher level of aerosol particles that we have in Europe then. And then we have a brightening period when the aerosol particles start to reduce after approximately 1980 then, during the latest 4 decades. So it's time to present the method we have used now. based on the change in the radiation to estimate a warming indirectly caused by a reduction in the aerosol particles. And here is the radiation balance that we can play with. We have the solar radiation, we have the surface reflection, we have energy that are converting to infrared radiation that I mentioned for you. We also have the heat flux, which I will soon coming back to, but I will leaving that for a moment, because when we're estimating the warming, we are applying this simple relationship, Stefan Boltzmann's law, as you see here. And this relation relate on the left radiation, and in our case, the change in the radiation to a warming, to a temperature increase on the right. Sigma here is Stefan Boltzmann's constant. But before applying this relationship, the equation that we see here to estimate the warming, we have to reduce for surface reflection that disappear, that are not used by the planet. We also use for heat flux then. So then I would like to show you results based on this method that we're using here. But just to remind ourselves about the conditions that we have when we're comparing the latest decades with the 80s. So in this figure here on the left in aerosol optical thickness, you see a drop, a reduction in the aerosol optical thickness. And this is for all sky conditions. We start with that. And we take a look at era 5, the changes in the radiation that we get according to this drop in aerosols on the left. So in the middle figure, we see this increase in the surface solar radiation in watt per square meter then. And then we finally applied our method to estimate the warming for Europe according to this latest 4 decades. And once again, is according to the half summer year, an average according to April to September. And what we get in increase in the temperature approximately around 1 degree for Central and Eastern Europe. So it's not a small number, what we see here in the warming, in a masking effect that aerosols have had for Europe. We can do the similar thing now for all sky conditions. And on the left, we see the changes in the radiation according to the current period. And on the left, we have estimated the temperature increase. And also for Eastern and Central Europe, we have the strongest increase in the temperature, as you see here. Approximately also here around 1 degree, maybe a little bit more also compared to the clear sky condition. Since we're dealing with all sky conditions, it could be worthwhile to take a look if we see any change in the cloud for Europe. And this is a low cloud cover. And when we take a look at this figure and comparing the 80s with the latest decade, we see for large part of Europe a reduction in the clouds. And we could start to think about if we have any reasons for that. And one reason that probably could have influencing the cloud, what we think, is what I mentioned before, that we have getting a drier climate in Europe. And therefore, I would like to focus a bit about the trends that we have in the heat flux. And you may ask now, what is heat flux? You can see heat flux at the energy that the surface are absorbing, and it's a mechanism. This energy is a mechanism then to warm up the atmosphere. But this warming can occur differently depending on where the energy is converting to, because on the left we see sensible heat flux, and then you have a direct heating of the atmosphere, and particularly then the lowest part of the atmosphere. But heat flux consists also of latent heat flux, and that is evaporation that are producing the water vapor that we get into the atmosphere. And when you're comparing this 4 decades now, we see a shift in the heat flux. So we get more of sensible heat flux and less of latent heat flux, less of evaporation and water vapor. And this is particularly the case for southern part of Europe, including Iberian Peninsula, Spain and Portugal and France, as you see here. So what we believe is that the drier climate that we have now at present day probably also have influencing the clouds in the atmosphere, that we also see a lower amount of clouds due to lower amount of evaporation and water vapor. So what is the reasons for this shift in the heat flux? Think about it. During these 4 decades, we have enhanced greenhouse effect. More of infrared radiation are reaching the ground. But if you remember, part of Europe have also a strong reduction of the aerosols. So simultaneous to that, we get also more of solar radiation, and more energy available at the surface is heating the surface and drying out the surface. So that's an explanation that we get for this positive feedback and a drier climate, particularly a drier surface. I should also now show you the results of the total warming that we have for Europe. And once again, Europe is the continent that are warming up fastest among all the continents. And here we see the warming based on our study, subtolerated according to clear sky conditions on the left and all sky conditions on the right. And I have marked out where I'm living, and many of you also living in Stockholm, because when you take a look at this figure and go further north of Stockholm, if you go further north of Stockholm, all this warming that are occurring in the Bay of Finland, northern part of Baltic Sea and the Arctic region, this is explained by decline in sea ice. So here we have a strong reduction in the albedo effect. You can see it as a positive feedback, but it's not so much connected to aerosol particles. It's more a result of the global warming, the enhanced greenhouse effect, and the albedo effect. If we go south of Stockholm now and take a look at the rest, the remaining part of Europe, so here we have a combination of the global warming, the enhanced greenhouse effect, and also reduction in the aerosol particles. But one important thing also that we also have getting a positive feedback associated with drier surface conditions that we have got, particularly as you saw in the previous figure for Southern Europe then. So what we see here in the total warming over large part of Europe is up to 2 degrees or a little bit more, nearly a double speed of the warming according to these 4 decades, I should mention, if you compare this to the global warming record, which is approximately 1.2 degrees warming according to, during the industrialization. So this is a much longer period then. Yeah, so our fast warming that we see in this figure, we have also confirmed this with in situ measurement. And I mean, this goes in line with IPCC is presenting about the warming. And if you take a look at the left figure here, this is a temperature increase when the IPCC have separated according to land and ocean, as you see. And together with our study, and when I saw these results, it was surprising for me, because when you go back 10 years in time, it was not so clear that the warming goes much, much faster over land than over the ocean. And one reason for that is that much of the heat, most of the heat, I would say, has been taken up in the ocean, but there you need to distribute the heat over the full column that you have in the ocean. The land surface is a narrow surface that are redistribution the energy much, much faster. But this was really a surprise that the warming over land goes much, much faster over land compared to the ocean, because we didn't see it so clearly 10 years back in time then. I've also included ECMWF era 5 here on the right, according to global annual mean temperature increase. And the good thing with era 5 is that now we also have data back to 1950. We didn't have that in our study, so it's very new actually that they have finally released this reanalysis back to 1940. So before it was 1980 that we play with the data and results in our publication. But you see here, according to this approximately 8 decades, we have a warming over land 1.4 that are very much agree with what IPCC are presenting on the left. Then. Finally, I will present a summary of are mainly based on our study then articles. So the unmasking the aerosol effects gives a substantial warming over the latest 4 decades over Europe, about 1 degree over central and eastern part of Europe. But keep in mind, so this will be history for Europe, I would like to say, but aerosols are today masking warming at other regions on Earth. The total warming over Europe is about 2 degrees over a large part of Europe. The strong warming over Iberian Peninsula is likely also explained by reduced evaporative cooling. This is the change that we have in the heat flux. And when we have a reduced evaporative cooling connected to reduced evaporation and reduced water vapor, at the same time, we have increased sensible warming that directly warming up the atmosphere. And this is likely positive feedback due to the global warming. So the final part that we also included in our article is that large efforts are needed to mitigate climate change in Europe, and anthropogenic carbon dioxide is of particular serious concern since, as I mentioned before, it continues to affect climate for hundreds to thousands of years now. Okay, thank you. If you're still listening, they're back. Okay.
Thank you very much indeed, Paul, for that excellent talk.